we will talk about fairness of executions. We are usually interested only in executions of a composed input-output automaton in which all components get fair turns to perform steps. Each input-output automaton groups its locally controlled actions into tasks. And in this case, fairness means that each of these tasks gets infinitely many opportunities to perform one of its actions. So a task T is a set of locally controlled action. Remember, locally controlled actions are output actions and internal actions. And a task corresponds to a thread of control used to define fair execution. And fairness means that a task that is continuously enabled gets to make transition steps. That is what it means. And we need this to be able to prove progress properties of systems and algorithms, of course. So let us see a formal definition of fairness. So formally, an execution, E, or a fragment of that execution of an automaton A is fair to a task T if one of the following condition holds. So what are the conditions? The first case, the execution is finite and T is not enabled in the final state of E. So a task T is not enabled in the final state of E. Second, E is infinite and contains infinitely many events of T, then that is a fair execution. The third case is that E is infinite, but it contains infinitely many states in which T is not enabled. The conditions on the actions are basically false. And an execution is fair if it is fair to all tasks of the automaton A. And we use the notation fair execution of A to mean it is a set of fair execution of the automaton A. And we say a trace of A is fair if it is a trace of a fair execution, and the set of all fair traces is denoted by this notation. So let us now look to an example and see what is going on. We had this example of a channel, and we said that the message set is 1, 2, and we showed 3 possible executions and corresponding traces. So let us look to the first execution. It is a finite execution with a send followed by deliver, a send followed by deliver. Now, at this point, that is a final state. In this final state, there is no locally controlled action that is enabled. So this is fair execution. And the corresponding trace is a fair trace. Now let us look to that other one. So this is the next execution is a fragment of the first one. But at this state, there is one task enabled. This is a task that can deliver the message. Therefore, this execution is not fair. And the corresponding trace is not fair. Now, the third execution is an infinite execution. This infinite execution has only send actions. So at this execution, the tasks to deliver the messages that has been sent are always enabled, and they have infinitely many chances, but they are not executed. And therefore, this infinite execution is not fair. And of course, the corresponding trace is not fair. Now let us consider another example that we have seen. It was the example of a distributed system. We had a system consisting of a number of processes and reliable unidirectional channels between them. These are n-square unidirectional channels. In every fair execution of this system, every message that is sent is eventually delivered. We don't know when, but it will be delivered in that execution. Second, in every fair execution containing at least one init I event for each pi. Remember, these were init were coming from the environment. And if it contains one init I for each event, it means the init will fill the corresponding element in the local val vector. And once this element is filled, then send actions will be enabled. So each process sends infinitely many messages to each other, because once each process element in the vector is filled, the send actions are always enabled. So they can send the same values, or if the values is filled again, send the new values and so on. And in every fair execution, each process performs infinitely many decide steps, because the condition on a decide step or a decide action was basically that the whole vector is filled with values that are defined. There is no undefined value in the vector. This was the condition, and therefore a decide action can always be performed. So this gives us a description of this distributed system. And the fair execution, these are the ones that we are interested in. There are some results that direct follows from the theorems that we had about execution, and this can be just imported into fair executions. So these are results that we have talked about before. I will mention them very quickly. That fair execution or a trace of a composition projects to yield fair execution of traces of the component automata. And the theorem was as follows. We have seen that before. We have seen this. Just now we are using fair executions instead of executions and fair traces instead of traces. So if E is a fair execution, then projecting E into the component automata, AI, is a fair execution of the component automata. And if beta is a fair trace of A, then projecting beta into the component automata, AI, will give a fair trace of AI. Next, fair executions of a component automata can be pasted together to form a fair execution of composition. So what are these again? Suppose EI is a fair execution of AI, and beta is a sequence of external actions. If you project beta into each component AI, and we get a fair execution of AI, then there is a fair execution of the composition E. We call it E, of the automata A. And what properties this fair execution has? It has the following property, that beta is a fair trace of E, and the local execution of its component automata is the projection of E into the component AI. And the last property is that fair traces of component automata can be glued together, pasted together to form a fair trace of the composition. So if beta is a sequence of the external actions of A, so the projection of beta into a component automata, if that is a fair trace of AI, then for all AI, for all components, beta is a fair trace of the composition.